Hello there, and welcome to these next two sections in Chapter 12. These are sections 12.3 and 12.4 on what are known as the dot product and the cross product. So in this video, we're going to begin our discussion of the dot product. So to start, let's look at the dot product in R2. So let's say we have two vectors, a and b, and in component form, a is a1i plus a2j, and b is b1i plus b2j. Okay, so to form what we're going to call the dot product of a and b, and note this notation here, a dot b, hence the name dot product, this is equal to a1 b1, which is just the product of the I components of these two vectors, plus a2 b2, which is the product of the j components of these two vectors. All right, now we can extend the definition to R3 quite naturally. Here we're going to multiply the I components to get a1 b1, the j components to get a2 b2, and the k components to get a3 b3, and sum those products, and that sum there is the dot product. All right, so notice here that when you take two vectors a and b and form their dot product, the output here is a scalar, right? a1, a2, a3, and b1, b2, b3, these are the components of our vectors, and so they're just real numbers. Okay, so this expression you see on the right-hand side is in fact a scalar, right? It's just a real number. So for that reason, the dot product sometimes is referred to as a scalar product. All right, so let's get two quick examples. Let's say a is the vector 2i minus 3j, and b is the vector I plus 4j minus 5k. So to form their dot product, multiply the I components, so 2 times 1, the j components, negative 3 times 4, and the k components, and note here that since you do not see k in the expression for the vector a, that's just saying that the k component is 0. So there we get 0 times negative 5, and this simplifies to the scalar negative 10. All right, another example here. I have the vector a, which is 5, 0, negative 3, and b, which is 3, 4, 5. And so to form their dot product, okay, multiply the I components, 5 times 3, the j components, 0 times 4, and the k components, negative 3 times 5, and this simplifies to the scalar 0. All right, great. So now let's go ahead and look at some properties of the dot product. And so the first property you see here says that a dot b and b dot a are the same. So in other words, the dot product is a commutative product, which is, of course, the same thing that we have for ordinary multiplication with real numbers, right? 3 times 5 and 5 times 3 are both 15. Okay, so reversing the order of multiplication here when you're using the dot product gives you the same output. Now to prove that, okay, a dot b, this is a1 b1 plus a2 b2, and since a1 b1, these are just real numbers, as we just noted, ordinary multiplication of real numbers is commutative, so a1 b1 and b1 a1 are the same thing. Likewise here for a2 b2 and b2 a2, you see this expression right here is just b dot a, so that's the end of the proof. All right, for this next property, it says that the dot product is distributive, and so if I have a dotted with the sum of two vectors, b and c, this property says that I can distribute the vector a, and it will multiply, using the dot product, these vectors b and c as follows. A dot b plus then a dot c. Okay, so this looks just like the ordinary distributive property of real numbers. And to prove this property, well, if I write a in component form, this is a1i plus a2j, and b plus c in component form, that's b1 plus c1i plus b2 plus c2j, and you take the dot product of these two vectors, well, multiply their I components, so that's a1 times the quantity b1 plus c1, and then multiply their j components, so a2 times the quantity b2 plus c2, and then sum these two products. And now I'm going to go ahead and apply the ordinary distributive property of real numbers, right? So distribute the a1 and the a2, and that gives us this expression. And now grouping as indicated, okay, in orange we have a1 b1 plus a2 b2, well that's just a dot b, and a1 c1 plus a2 c2, that is a dot c, so that completes the proof. All right, and then For this third property, this says that A dot, a scalar multiple of B, so here S is a scalar, is equal to that scalar S times the dot product of A and B. So in other words, we can take the scalar S and just pull it out in front. So to prove this property, well, write A in components, A1i plus A2j, and S times B in components. That's where we just scale the components of B by S, so SB1i plus SB2j. And now to take the dot product of these vectors, multiply their I components, so A1 SB1 plus, okay, the product of their j components, A2 SB2. And now we can go ahead and factor out S, which is really the reverse of the distributive property for ordinary real numbers. So you get S times this expression, and this expression in parentheses is just A dot B. So that completes the proof there. And then for this last property, which is, note here, starred, okay, put stars around it to just emphasize that this is one of the most important properties of the dot product, and something that we're going to see come up a lot down the line. So it says that if you take a vector and you dot it with itself, so A dot A, that gives you the square of the magnitude of that vector. Okay, so we can prove that as follows. So writing A in component form, this is A1i plus A2j. If I dot it with itself, well, multiplying the I components gives me A1 squared. Multiplying the j components gives me A2 squared. So here I wind up with the sum of the squares of the components. And if you recall how we compute the magnitude of a vector in terms of components, that's equal to the square root of the sum of the squares of the components of the vector. And since I just have the sum of the squares of the components without the square root, this in fact is equal to the square of the magnitude of the vector A. All right, great. So now let's turn to another really key property of the dot product, and this deals with the geometry of the dot product. Okay, so let's say I have two vectors A and B, and I'll denote the angle between them as theta. And here notice I'm making this restriction that theta varies from 0 to 180 degrees, including 0 and 180 degrees. So why am I making this restriction? Well, basically it just allows me to avoid any ambiguity in referencing the angle between the vectors. So let's say the vectors are positioned like this. If I say, well, what's the angle between the vectors? Am I referring to this angle here or this angle here? Well, by this restriction, I must be referring to that angle right there, right? The angle between 0 and 180 degrees. Okay, so now with that in mind, let's go ahead and look at the key result here. It says that A dot B is equal to the product of the magnitudes of the two vectors, so magnitude A times magnitude B, times the cosine of the angle between them, so cosine of theta. All right, so to prove this, let's go ahead and form this triangle where this side in orange that runs from the tip of B to the tip of A, well, that is just the vector A minus B. And since for a general pair of vectors, A and B, this triangle won't necessarily be a right triangle, right? So I'm going to apply the law of cosines here to relate the sides in this angle theta. And recall what the law of cosine says. It says that the square of the side opposite this angle theta, so that would be the square of the magnitude of this vector A minus B, is equal to the sum of the squares of the other two sides, so that's magnitude A squared plus magnitude B squared minus 2 times the product of the lengths of the other two sides, so magnitude A, magnitude B, times the cosine of this angle theta. All right, now what I'm going to do is rewrite this left-hand side using some of the properties above. Okay, so first, using property 4 that says the dot product of any vector with itself is equal to the square of the magnitude. Well, I have the square of the magnitude of A minus B. So, from property 4, that's equal to the dot product of A minus B with itself. Okay, now I can use the second property that says the dot product is distributive to open this up. Okay, this is essentially the same thing as squaring a binomial, but now we're using the dot product, right, instead of ordinary multiplication. So we have A dot A and then minus A dot B minus b dot a, and then plus b dot b. Okay, now coming back to property 4, a dot a, well, that's magnitude a squared. B dot b, that's magnitude of b squared. And then from the first property, well, a dot b and b dot a are the same thing, so in the middle there we really have minus 2 times a dot b. Okay, so now what I'm going to do is replace what I have here on magnitude a minus b squared with this expression we just derived, and so that gives us the following, right? Now, some really nice things happen. Notice we have the magnitude of a squared on both sides, so those drop out. We also have the magnitude of b squared on both sides, so those drop out, and so that leaves us with minus 2 times a dot b is equal to minus 2 times the product of the magnitudes of a and b times the cosine of theta, and now dividing both sides by negative 2, we are done. Okay, so what are some consequences of all of this? I'm going to go ahead and make a little space here. All right, oops, sorry, I need to get rid of that. There we go. And I'll leave that in just for our reference. So first note that if the angle theta is greater than or equal to 0 and less than 90, the cosine of theta is greater than 0. Okay, so looking at this result, this says a dot b is the product of the magnitudes of a and b times the cosine of theta. Well, the magnitudes, right, are always non-negative, right? And the cosine of theta, if that's positive, and these two vectors are both non-zero, that means, right, that a dot b must be positive. Okay, so a positive dot product indicates that the angle between the vectors is acute. Okay, that's the big takeaway here. And then a similar argument, well, if the angle theta is larger than 90 degrees but less than or equal to 180 degrees, and we note here the cosine of theta there is negative, well, again, if both a and b are non-zero vectors, right, their magnitudes are positive, and if the cosine is negative, that means that a dot b is negative. So a negative dot product indicates that the angle between the vectors then is obtuse. All right, and so then right in the middle of those two scenarios is when the angle theta is 90 degrees. So in other words, when the two vectors are perpendicular, which is also to say that they're orthogonal. Okay, so state this is a theorem just because it's so important and useful. It says let a and b be non-zero vectors, then a dot b equals 0 is equivalent to the angle between them being 90 degrees, which is equivalent to saying that a and b are orthogonal, or in other words, perpendicular. And we can denote that two vectors are orthogonal using a shorthand notation where here we use this upside down t there. So this is telling us that a and b are orthogonal. All right, so now what's an example of that? Well, we actually already saw one, right? Going back to these vectors, a and b, where a is 5, 0, negative 3, and b is 3, 4, 5. Okay, we saw before that their dot product is 0, and so that tells us that these vectors are in fact orthogonal. All right, well, that's a great place to stop. We'll pick up with more of this in the next video. Thanks so much.